Hi, this is Dr. Asan Abdullah with the course Complexity and Analysis of Algorithms. So, the topic which we are covering is sorting, and which is topic number 8 in the table of contents of the course. And the subtopic is divide and conquer sorting algorithm. So, therefore, be here. So, the supplemental material for this course is available at easymcq.com/goget, which is basically a personalized learning management system. And why it is personalized? The reason being that it allows you to personalize the way and the mode and the route which you would like to take to learn from this course. And how you do that, that is shown in video number 1 of this LMS. And you can also personalize the interface, how it appears, the color, the font, the size, the distance, and everything, so as to enhance your learning experience. How you do that, that is shown in video number 4. And you can have your own personalized tests, okay, which are graded, and the analysis of the overall results is also provided, so that you know your level of learning. How you do that, that is shown in video number 5 of the learning management system. And of course, there are other videos which show you how to search, how to do advanced search, and all some useful features. So, and of course, the videos of the course are also available online. And where they are available on Canvas, and they are also available on my YouTube channel. So, if you go to YouTube and type my name, Dr. Asan Abdullah, you will find these videos which I have just mentioned, and you will also find the course videos for this course and other cutting edge courses. So what are the table of contents which we are covering in this course? They are in front of you, and right now we are at the topic of sorting. Okay, and we'll also cover some very exciting and advanced algorithm topics, which are randomized algorithms, approximate algorithms, and genetic algorithms. So now we move on to the supplemental website. So we are at the supplemental website. So up till question 6 has been covered in lecture 8A. So now we are in lecture 8B, right? Because that was for the basic sorting algorithms, and now we are looking at the basic divide and conquer sorting algorithms. So they're different. And what we are looking at in this question is the working of these algorithms and their application domains. Because all these algorithms, they are just like tools, and you should be knowing that which tool to use where and how to solve the problem more effectively and efficiently. So the basic sorting algorithm which we will be covering in the domain of divide and conquer, they are merge sort, basically, which divides keeps on dividing the data to be sorted until it's down to the base case, and then starts merging them. I'll explain this. And then we have quicksort. So what quicksort does, that there is a pivot, and all the numbers which are greater than the pivot are moved to the right, and which are left are the ones which are smaller than the pivot, and this is done recursively. So the list gets sorted, and heap sort, basically it results in generating a binary heap. So this is not purely divide and conquer, but this is a good comparison. So now let's look at the description of the answer. So how does the merge sort works? The merge sort works by, we have the data set or the input, which is split into smaller sublists. And this keeps on splitting recursively till we reach the list which consists of only one element. So we have n, say for example, we have n numbers. So we keep on splitting till the list consists of a single element or number, and then those numbers are merged. Okay, so when two numbers are merged together, so we have sublist of size 2, which is sorted. And this keeps then, and this keep on repeating this process until there's only one sublist left, which is the sorted one. So it's a very elegant way of sorting, and it is used where stability is crucial. Okay, so this is stable sort, right? And what are the application domains, such as in database systems or the applications where sorting linked lists? Stability is important. And of course, data sets or external sorting. Why external sorting? Because the data set is so large that it does not fit into the main memory of the machine. It does not fit there. Okay. Therefore, to handle such large data sets, right, this has to be done in the form of chunks, and that has to be done sequentially. But by the virtue of that, the merging property, this sequential merging, which goes outside the memory, then comes inside the memory, that works. So that is the beauty of this approach. So then we have quicksort. So quicksort, there is a pivot element. There is a pivot element, and what happens is that the data is partitioned in two parts based upon the pivot element. Now that pivot element, so all the elements which are smaller than the pivot, okay, they go to one side of the list, and which are larger, they go to the other side of the pivot. And this process is repeated recursively. And what happens that in the end, the entire list is sorted. Okay. So this is in place sorting. It means that it does not require extra storage, which was required for merge sort. Okay. Now, one thing is very obvious here is that the choice of the pivot plays a crucial role in the of course the result would be same. So if I use merge sort, if I use quick sort, if I use heap sort, the result would always be the same. It would be sorted, right? But there are subtle differences such as the stability, which we will discuss. Okay. So the choice of the pivot is critical, which we will discuss. So what are the application domains of quick sort? Okay, environments like embedded systems. Why? Because it does not require a lot of memory, right? Database and file systems. Okay, when memory usage is a concern, that is the so when memory is not at the premium, then quicksort is good option because it sorts in place. It does not require additional storage. Okay, so usually we can figure out the application domain. So for example, if I'm using some very small machine, maybe I'm using Raspberry Pi or something like this, then probably I'm better off using quicksort because it does not require a lot of memory. Okay, then heap sort. So heap sort basically these the quick sort and merge sort had the data set in the form of a list, but which is very interesting in heap sort that it transforms the list into a binary heap structure. So instead of a list, there is a binary tree. Now remember that the binary tree is an abstract data type. The binary tree is typically implemented using an array. Okay, so and usually it's a max heap in ascending for ascending order. Max heap means that the root is the largest value. And how it works, there is a question in which I'll show in detail how does the heap sort works. And of course, if you type heap sort in square brackets on the main page, you can find a lot of stuff. Or if you go to the course which is data structures, algorithm, and generic programming, there's a whole topic on heap sort. Probably I don't know, maybe 10 more than 10 questions and corresponding answers. So this is repeated. You remove the root, okay, and swap the root with the last element. Swap the root of the heap, the last element, and then there's something called which is called as the heap property or the heapify. And then of course the size of the heap decreases because one element has been removed, and this is continued till the heap is empty and you have a sorted list, right? So the application domain is again in place sorting, right? And there is no concern of stability. So for example, priority queues and resource scheduling. So and it does not require additional memory. So it's with the memory is premium, it is a good choice. Such a real time or embedded systems. Okay, and of course it is kind of obvious that this is not such a straightforward to implement. We'll go over this. So now let's look at some more interesting stuff. So compare and analyze the time and space complexity. So now we're getting real of these three basic divide and conquer sorting algorithms, which was merge sort, quick sort, and heap sort, and list their pros and cons. So now we compare them on technical grounds. Okay. So merge sort time complexity is order n log n, right? And the beauty is that this is the best average and worst case. Merge sort is always n log n. Okay. And the performance is consistent. Consistent means that it never drops to order n square. The which is for example the space complexity is order n. This space complexity in addition to storing the list. This is in addition to the list. So the good thing about is that it is stable sorting. Okay, and it is efficient for large databases. Efficient in the sense that the time complexity is always order n log n. It is precise. It's good scalability and predictable performance. We know it's always going to be order n log n. But the cons are obvious that it requires additional memory for merging in addition to the storage, right? So that the efficiency in the or for the large data sets kind of gets bumped over here and affected for because of the merging. And the practice in practice it is kind of slower as compared to other algorithms for smaller data sets. Why? Because due to the overhead. So when the data set is large, so the cost of the overheads is amortized across the entire data set. Okay. So quicksort. So quicksort, there's a catch. So order n log n on average. Okay, but in the worst case, as I mentioned before, when the pivot selection is not a good choice, it can degrade to order n square. Pivot selection means that if at every iteration too many elements have to be moved across the pivot and only one element gets sorted. So this is straightforward. So you have n minus 1 comparisons, then you have n minus 2 comparisons, and so on up till 3, 2, and 1 comparisons, which is n into n minus 1 divided by 2, which is order n square. So this is the worst. So one has to be very careful. So we'll spend some time on the pivot selection and the issues of quicksort. Okay, and of course the space complexity is order log of n. Why it's log of n? Because of the recursive implementation. We have covered this in a lot of details, right? So it does not require additional storage for sorting. It is in place sorting, but when the recursive call is made and the data and the control variables, they are placed on the stack, that occupies space. So since it's n log n and there is no extra storage requirement other than recursion, so it is good. It is fast for large data sets, and since it's in place sorting, so there's no additional memory required, and it is well suited for average case but not the worst case, because worst case is the con that becomes order n square because of the bad choice of pivot. But there are many ways of getting a better pivot to get good performance, and it is not stable. It means that, as I've already discussed in the lecture 8a, showed you a picture also, that because of that random of that selection of the pivot, so to say, so there is randomness here. So the stability is not ensured. All right. So let's move on to heap sort. So what happens in heap sort is that heap sort, basically the time complexity is order n log n, right? And the space, this is the space complexity, means that in addition to the space required to store the data set. Okay. So that's order 1, so that's independent of the size, and there is this is in place sorting. Okay, it's fine. So there's no extra memory. This is good. Always on order n log n time, right? So there is no issue of n square like in quicksort. And ideal for environments where memory usage is critical. Okay, this is fine, but that is not stable. This is not stable, right? Like merge sort is stable, quicksort is not stable, and heap is also not stable. And if you look at the constant values, so quicksort with all its shortcomings, okay, uh, heap sort is slower than quicksort because of the constant factors, and it is more complex to implement than the other sorting algorithms which we have just looked at. So let's look at let me zoom this and we compare these sorting techniques. So the zooming will help a lot. So we see that merge sort is divide and conquer, and quicksort is also divide and conquer, but heap sort is binary heap. They, of course, they all three of them are comparison based. Okay, so best case is for all of them, are best case is order n log n. This is fine, and average case they are also n log n. This is also fine, but quicksort is kind of tricky. It's order n square. Space complexity, which is the additional space. Merge sort requires order n space for the sort for the merging, and this requires order 1 for a heap sort, and for take care of the recursion, right? Because the data is getting divided. Best case scenario, right? So there are order log n size of the memory used for recursion, required for recursion. Okay, merge sort is stable, but quick sort and the heap sort, they are not stable. In place sorting, so you see that there are quite a few differences. Okay, so some of the strengths in there are in one technique, and there are certain issues with other technique. For implementation complexity, right? So it is moderate for merge sort, moderate for heap sort, but it is moderate to high. Why? Because of the to take care of the pivot issues, because then it will degrade the performance. Adaptability to data for large data set, it is good. So efficient but slow if the data is already in the form of a heap, right? And because you are doing it, repeating things, performs poorly on already sorted data. Quick sort. So the data is say in ascending order and you want to bring it in descending order, that's a nightmare. And the use cases are here. So you see that each of these techniques, they have their own pros and cons, and one has to be in the knowledge and aware of them. So what is heap sort and how does it works? So I promise that I will explain heap sort to you. So in heap sort, Heap sort is of course comparison based sorting technique, and it uses a binary heap. I will show you a picture also. It uses a binary heap. So basically is a start with a binary tree. Okay, and we may be creating a binary tree, or we store it in a binary tree and heapify it. Okay, and of course it is in place, so it doesn't require extra memory. So first we create a max heap in ascending order. It could be a min heap also in descending order from the array of the elements, and then repeatedly remove the root. Okay, we move the root and replace it with the last element, right? And this is repeated. Now I'm not going into a lot of details of how heap sort works. As I said that you can go to the main page, and in the yellow box type in square bracket heap sort, you will get everything. Or you can go to the course data structure and algorithms. There's a full topic on heap sort. Okay, so so heap construction is called as heapify. So we have the input array into a, we convert. Heapify is the conversion. Heapify is conversion of the input array into a max heap or a min heap, and that takes order log and time, right? Because what happens is that you bring you remove the root, which is the smaller or the largest depending upon min or max heap, and then you replace it with the last element. And in the worst case, what happens that there is a shuffling and there is a movement from the root to the leaf, so that takes order log and time. Okay, so it is heapified, and this is explained here. So when the heap is there, repeatedly remove the root element, right, which is always the largest one or the smallest one, and swap it with the last element of the heap, and that reduces the heap size and maintain the heapify property, obviously. And you keep on doing this until all of the elements have been removed. So it's the complexity is fairly simple, because one iteration of settling takes log n time, order log n time, and this is to be done order n times because there are n elements. So the time complexity is order n log n, and the beauty is that this is order n log n, best case, average case, and worst case. Okay, so this is the beauty of it. And the space complexity is order 1. So here, okay, I will zoom it for you. So basically this is the array in which we have stored the tree, right? And we know how to get to the child, the left child and the right child of the tree. Okay, and so this is at location 1. So the left child, the immediate left child, is at location 2 I plus 1, and the next child is at location I plus 2. Okay, so this, so the right child of 7, which is location at location 3, will be at 3 plus 2, which is at 5. So this is covered in the topic of trees in data structures and algorithms. So this is the initial elements of the binary tree, and this is the max heap. So the max heap is showing that the root is the largest element among all its children, and as you can see that it is true recursively. 4 is the largest among all its children, and 7 is the largest among all its children. This is done recursively. This is true recursively. Okay. So we finish this with a animation showing the working of heap sort. So let's look at this animation. So click view description for the animation. So I click over here. So just look at it, and this is just what I explained is shown here. And basically, first of all, the tree is being generated, right? And the tree is generated as per the array is accessed, and then it is heapified. All right, it is heapified also, right? So see that the parent is greater than the both left and the right child. All right, so which is shown swap here. Now what happens, we take out the all the values, right, from the binary tree. Okay, this is not yet sorted, remember, don't consider it sorted. And then we compare them, right? We remove the root. Okay, and when we remove the root, the shuffling takes place, and then the sorting takes place. Okay, so this is how the sorting takes place, and keep on doing this till it is sorted. Okay, I hope you've enjoyed it, and with this I'm going to end this video on the divide and conquer sorting approaches. Okay, it's still some iterations to go, and yes, it is sorted now. Thank you very much.